Modern turbochargers are based on a simple principle. If the air entering an engine is pressurized and more oxygen forced in, then, by adding more fuel, the result is higher engine torque and more power. At sea level, there are 0.016 pounds of oxygen per cubic foot. At higher altitudes, the air is thinner, so there is less oxygen available. For example, at 5,000 feet, there are 0.013 pounds of oxygen per cubic foot. And at 15,000 feet, there are only 0.01 pounds of oxygen per cubic foot. So, as altitude increases, it becomes more difficult for an engine to obtain the mass of oxygen it needs to generate its required power. In a naturally aspirated engine, the only force pushing air into the engine is the ever-decreasing atmospheric pressure. With less oxygen available for combustion, the fuel is only partially burned, and some escapes out of the exhaust as black smoke. A turbocharger helps to supply air by forcing it into the combustion chamber under pressure. It is able to do this since the reduced atmospheric pressure makes the turbine stage more efficient. Thus, the engine can maintain virtually the same air-fuel ratio as at sea level, with almost no change in either power output or exhaust emissions level. Turbocharger technology evolved from mechanically driven superchargers, which create boost pressure using a mechanical pump driven directly from the engine. However, the inefficient supercharger is an engine parasite. It uses a large proportion of the potential power increase to drive itself. For example, a supercharger that could, theoretically, raise a 220 horsepower engine to 370 horsepower could only manage 320 horsepower. The supercharger itself absorbs 50 horsepower. Because a turbocharger is able to utilize both the pressure and heat energy of the engine exhaust gases without taking power from the engine, it is far more efficient. It's this benefit that inspired Holset to begin developing turbocharger technology in 1954. And this is also the reason why most diesel-powered trucks have turbochargers today. Inside a turbocharger, exhaust gas is channeled through the turbine housing, where it increases speed. The gas then flows through the turbine wheel, where it slows down again, releasing energy. The turbine wheel drives the common shaft that connects it to the compressor wheel. The compressor wheel draws filtered air into the compressor housing, raising both its pressure and density, and forces it into the engine. The center housing contains precision, fully floating journal bearings. The bearings ride on a film of oil to keep the turbine and compressor wheels turning smoothly at high operating speeds. Also, at both ends of the center housing are oil seal rings, often called split ring seals or piston ring seals. These rings, in conjunction with careful control of the gas pressure differences on either side, help to ensure that the oil does not leak into either the compressor or turbine casings. The center housing also contains a thrust bearing, oil slinger, oil baffle, and journal bearing retaining rings. The rate of airflow into the engine is controlled by the design of both the wheels and housings, and by the speed of the turbo, which automatically responds to changes in engine fueling. It is designed to help you increase your knowledge and skills of turbocharger failure diagnosis. Firstly, let's look at some of the on-vehicle symptoms that are commonly linked to turbochargers, but in many cases can be engine-related. There can be many causes of low power, low boost and black smoke. The driver won't be happy with any of them, but before taking the major step of removing the turbocharger, there are a number of on-engine checks that could save you time and money. Firstly, check the throttle linkage adjustment is correct. Check the injection pump, fuel timing and delivery is correct, and check the injectors. Also check the fuel supply is not restricted. Check the intake or exhaust systems are not restricted, and check that there are no restrictions through the air cooler. If all these are problem-free, then you'll need to check the turbocharger. Firstly, check that the turbocharger rotor rotates freely. Then check that the axial and radial clearances are to the specifications in the Halset Service Repair Manual. If the turbocharger model has a wastegate, check its operation by applying 3 bar or 45 psi air pressure. If you still have low power, low boost or black smoke, remove the turbocharger for closer inspection. If the problem is oil leakage or carryover, again check the turbocharger rotation and clearances. Check for restrictions in the air intake and oil drain. If the problem is noise, listen carefully and try and identify how it sounds. If it is a loud cyclic knock or surge, check the compressor intake and outlet for restrictions. If it is a high-pitched screech, scream or howl, check for exhaust gas or compressed air leaks. Remove the air intake pipework and spin the rotor to check for excessive clearance. Check other areas of the engine to locate the source of the noise. If it is not a leak and the sound is metal-to-metal contact, again the unit should be removed for further evaluation.